Hey guys, it's AxiomaticUncertainty here, and I'm back with another video. And today I'm going to be talking about this 2x2 Rubik's Cube solver that you can see here. Um, I am using a star search with a deep neural network in order to try to solve the cube in as few moves as possible. Um, Unfortunately, due to restrictions on my compute, just because I have kind of an older computer with very little space to install CUDA and stuff like that for my GPU, um, I wasn't able to train a large enough model to make this work with a 3x3, but with a 2x2 it works fine. Um, so the first thing I'm going to do is I'm just going to enter a scramble, and we'll have that chug along while I'm explaining things. So the first thing I want to explain is, obviously I'm not going to necessarily go over the cube itself. I think that that's pretty straightforward, and I also think that that gets a little bit, into the weeds of Rubik's cubes. Um, but what I will talk about is these two files, reinforcement and then the solver. Reinforcement, as you can probably guess, is the reinforcement learning file. This handles all the training for the models. So what you can see is we have this trainer class. Um, what we do is we first load the model. If the model doesn't exist, we create a new one. If we have to generate a model, what we're creating is currently this architecture, but this model architecture is actually too large. I was not um, really able to train with this in a practical sense. So actually the model that I'm using is like two layers, two hidden layers plus one smaller hidden layer. It's like 50 neurons. Um, and then basically that's the gist of it. We start out with this one hot encoded 2x2 representation. It has all the stickers. Um, and then we end with a value indicating an estimate of the number of states left to solve the cube. So, say we perform 2 moves, ideally this should predict 2. If we make 20 moves, um, on a 3x3 this should predict 20. On a 2x2 it should predict, however many moves it is from solved. Um, yeah, so that's pretty straightforward, I think. What we do then is we perform a training loop where we create a bunch of scrambles. For each of the scrambles that we generate, we record the number of moves made prior to where we are in the scramble, as well as the state of the cube, one hot encoded, and then we train it to predict the former from the latter. And you can see we just run training steps with a small batch size. Um, and at the end of it, we save the model each time. So that is the reinforcement learning portion. Now I'll get on to the actual solving portion. You can see there's some redundant methods here. Initially, I was working with this from a different angle, so I kind of built these brute force methods to go through and look ahead. With a two-way brute force search, we were able to look like 8 moves ahead, in probably like 15, 20 seconds. Obviously, you could do that a lot faster on a better computer, but I think that that's fairly reasonable. Um, but we don't need that. So instead, what we do is we first off instantiate our model, right? We load that into memory. We set this move priority variable, which defaults to 1. Basically, we're doing an A-star search, um, sort of, right? It's a mix of the cost of the existing pass, so the number of moves we've made already, plus the estimated moves remaining. So this is, if this is 1, this basically is an estimate of the total number of moves for this solve. That's how we know which moves we want to take a look at first. Um, and if this is a 0, it's looking exclusively at the number of moves that are estimated to be remaining. So it'll just go to the most promising state, meaning, if it's 80 moves in and it sees something good, it'll choose that over something that's 0 moves in and is slightly worse. So obviously you want 1 if you have enough compute, um, but you can also go somewhere in between if you're looking to sort of um, prioritize speed, but also have, a mix of speed and move prioritization. You could technically go higher than 1 if you really wanted to, just to um, even further decrease the importance of the heuristic and just turn it into a breadth first search as this goes to infinity. But yeah, the solving bit here takes a start state of a cube, it instantiates a set, which is a set of hashes of the one hot encoded states. This allows us to take a state and then predict how long, or I mean, how many times, if we've seen it or not. Sorry, I don't know why I screwed up there. Yeah, it allows us to predict if we, or to know if we've seen a state or not, so we don't just revisit states over and over. We one hot encode it, we predict the evaluation score for it, and then we take the state queue, which is essentially just a heap that contains all of the states that we want to look at in the future, and orders them according to this evaluation. Um, and then we just push on this value. Um, so yeah, we do all of this, and then we start our A star search. This isn't a true A star search because it's not guaranteed to be optimal because we don't have, um, as I may have mentioned, the ability to guarantee that our prediction is going to be below the actual number of moves. So this isn't guaranteed to find the optimal solution, it just tends to be close. But basically we want to check if the state is solved, right? If we've expanded a solved state, we output the number of moves in the solution. This is quarter turns of the cube. Um, we output the solution in actual text form, and then we output the number of states searched and discovered. Then what we're going to do is, this part is actually just legacy code. This is not necessary. We're going to go through all the successor states. So this is all 12 possible quarter turn moves from where we are. Um, and we're going to perform those operations, create a future state for each of them, and then insert them into our heap with their predicted scores as well. So you can see we're doing a prediction here. If it's solved, though, we insert 0 as the score. And if we wanted to, we could prioritize speed by just checking if these successor states are solved and then dealing with them instead. But I think that this is better to stay true to this move priority value. So we do that, and then obviously we have the cost, and we have an ID for this. This just prevents conflicts where we have multiple of the same thing being inserted into the heap, um, which, sometimes the evaluations can be identical. And then we take the current state, the future state, and the moves that we made, and insert those also. Sorry about that. And yeah, then we can add that to the list of seen states, and we just repeat this cycle as long as we need to until we find a solution. We have the main execution code, which just allows us to enter a scramble and then solves it. And this is really flexible too, because obviously you can see we can enter a model file, um, and if we wanted to, we could adapt this to work with any size cube, right? If the model supports it, it'll work, and if we give the start state more to work with, then it'll be fine. The only thing we would need to change is right now we're only turning the outer layers. This value here is the depth of the turn. So if we wanted to, we could actually enable making turns that are of a greater depth, to control sort of where in the cube we want to make these turns. So, if you have a 4x4, obviously you can turn the middle layers. Um, but yeah, you can see we ran that scramble that I talked about. It did all of this computation and it solved it in 14 turns, technically 13 since this F2 is being counted as 2 moves here. And you can see the solution that it gave us. I've checked some of the solutions manually. We're not going to do that here, but you can see it expanded, or it checked 143 states and it discovered 1,436 and evaluated all those. Um, and you can see in real time too, if I enter, say, like a really short state, like, right, if I enter this, this is 5 moves from being solved, shouldn't take long. I execute it, and you can see right now it's running. It explored 6 states, and it looked at 61 states total for evaluation. And you can see it solved it in 5 moves, and it gives us a solution here. Um, yeah, I think that this is really um, just a simple sort of solution to this problem. It's really interesting. Um, if you want to solve this more optimally, you could use an iterative deepening A-star search. I've seen some literature on this topic that's discussed that as well. And yeah, if you had a larger network, you could probably do this with 3x3s without much modification, but obviously I can't deal with that on my device. But either way, yeah, I just wanted to sort of go over this, talk about sort of my thoughts on it. I haven't made a video in a while, so I was kind of thinking that this might be a fun thing to do. But yeah, I hope you enjoyed this. I may make more videos in the future if things like this come up that are, you know, interesting enough to make videos on. Um, but anyways, I hope you enjoyed, and until next time, I hope you like, comment, and subscribe. If you have any video ideas, um, please leave those down below because I have basically none. So thanks for watching.